Today, we're going to be talking about personality type classification. In this project, we're going to be discussing how to classify emotions from 8 different categories: anger, surprise, disgust, fear, neutral, happiness, sadness, and contempt. These images were all extracted from a dataset that was found online. An example of one of the images in the dataset is shown over here. Obviously, this is a happiness image, and a lot of these images are exactly the same quality as this, grayscale and 350 by 350 pixels. Because some of the categories had more images than the other, synthesized images were created by changing factors such as the contrast, color, sharpness, and we added these to the categories with fewer images, such as anger, surprise, contempt, and sadness. This allowed for a more equal split of images for each separate category. In addition to this, we also split the data into training and validation datasets. This was on a 60-40 split because I determined that was the best ratio for splitting the data. And we also didn't leave any images for testing because there was already a testing dataset that was built into this GitHub repository. In the ending, there were around 4,000 images in each category for the training dataset, and there were around 2,730 images in each category for the validation dataset. I also resized the images from 350 to 3 by 350 to 50 by 50 for faster model training time, because the original model took a day to run, and by resizing the images, it actually took 5 hours to run, which shows that although it does lead to a lower accuracy, because the model does take a shorter time to run, it allows for more epochs, which allows for higher accuracy. So here's an example of the data pre-processing step that I did. So over here, I changed the images on 4 factors. So there's sharpness, contrast, color, and rotation. And I randomly selected how much I would apply of each to the images. So over here you can see that I randomly applied it. Then I did this on every single one of the images in the training dataset, and I made sure to do this multiple times depending on how small the folder was. So for instance, fear would have more of this processing step and will have more images created because there's so little of these images. While for example, surprise, which has 225 images, might have less of this processing step because there's so many more of this image. To make the most accurate predictive model, I determined that there were around 3 separate things that I could do, and I could see which one produced the best accuracy. The first one was using pre-existing Sagemaker image classification algorithms to produce the model. The next was utilizing AWS recognition to predict the personality of the testing images. And the last one was building a convolutional neural network from scratch using Tensorflow and Keras. So the first was using Sagemaker training jobs, which was the pre-existing Sagemaker image classification algorithm. So to do this, I shifted over some of the training and validation datasets to S3 for better operability. I used training jobs that had a 350 by 350 set, and I also used ML P2X large instance. Some of the most notable changes that were made to the hyperparameters that were set by default was that the number of epochs were changed to 15. The gradient descent method was stochastic gradient descent, and the number of training samples were 53,336. After training, the model's training time averaged around 5 hours. So after tweaking the model a bit, I determined that the best overall training accuracy that this model could provide was 88%, and a validation training accuracy of 81%. So to see how this model works on testing data, I took in the model that was created by the SageMaker training job, and I put it inside of a Jupyter notebook so we can make predictions on it. So I used MXNet to do this, and I took the image classification training job and I loaded it into an MX model, and I converted this MX model into a DenseNet prediction that we could then use to predict. This whole process is basically preparing making the prediction using the MX model, and then after that I was able to print out the unique emotion based on which testing image I wanted to use. So for instance, this one used the second image in the testing resize category. The next thing I did was use AWS recognition. So recognition is one of the most commonly used AWS models out there, and it accurately provides image classification capabilities. We focus on the emotion section of recognition, as this has the necessary information for predicting the personalities of the training images. So there was no necessary configuration to train this model. Rather than we just had to use the API to begin testing the model's accuracy immediately. So we decided not to use the training set, and I just decided to use just the testing set. So I ran the Boto3 client recognition model across all of the testing images, and the accuracy of the AWS model surprisingly was approximately 60%, which shows that it performed worse than the Sagemaker training job model. So if you see over here, there is this whole process is basically getting all of the different images from getting all of the different images and keys from the AWS bucket, and this step is actually detecting the faces using the Boto3 client. This last step checks through all of the emotions and checks through all of the documents and finds the best emotion. So that's how we eventually calculated this emotion classifier. The last step is building a CNN using Keras and Tensorflow. So using the Tensorflow and Keras libraries, a CNN model was made that would accurately predict incoming testing images that we had in the model. So again, we tweaked the hyperparameters. We made a CNN model that consisted of a combination of neural networks, convolutional, max pooling, and dense layers. And the main activation function was ReLU due to its fast computation runtime, and the hyperparameters were tweaked accordingly. Some of the most notable ones were 16 for the batch size, 12 for the number of epochs, and categorical loss entropy for the measure of loss. Over here, we took in the training and testing data, and this is actually training the model with the convolutional max pool and the dense layers. This last step just trains the model using an atom optimizer and a categorical loss cross entropy loss model. And this is already halfway through the model. And in this next step, we tested the built model, the model that we made using TensorFlow. And in the ending, after doing so, we achieved an accuracy of around 68%. So this was actually better than the recognition model and worse than the model that was trained with the Sagemaker training job. So this could only be trained with 50 by 50 training 50 by 50 images because the model took so long to run that we had to make it 350 by 350 so that the model ran in optimal time. So over here, each of the models are run on this new model predict, which is defined up over here, and based on that, we were able to determine how accurate this model really was. Some of the challenges that I faced during this project were that when we were training with TensorFlow and AWS SageMaker, there was a lot of constraints in terms of training time and accuracy of classification. So we had to convert the size of the images from 350 by 350 to 50 by 50 so that our model would train faster. SageMaker automatically logs out every 12 hours, so our effective training time is only reduced to that amount, so that makes it impossible to train any longer than that without our model stopping in the middle. Next, we reduced the size of our images, which significantly lowered our training and validation accuracy. Lastly, the accuracy of the dataset was pretty bad. So the accuracy of the classification, like I said above, was 56%, while our training accuracy was 98%. We made many changes to hyperparameters, including early stopping, learning rate, etc. And we weren't able to increase the validation accuracy, and the validation accuracy performed erratic behavior while training. So we found that even one of the best widely known image classification models had only an accuracy of 60%. showing that the dataset had inconsistent classifications or low quality images. However, due to our limited access of datasets, I was unable to procure a better one at this time, but we hope that our model will perform better with a more accurate dataset and scale linearly with the accuracy of the recognition image classification model, because it did perform as good as the recognition model. So, in overall, the main thing that I got away from this project was that's the Sagemaker training job image classification dataset does have the most accurate model to use, so that should be used at all costs because it allows you to effectively tweak your hyperparameters so it matches the project that you're doing. Recognition works for a general purpose, so you don't want to use that unless you're doing something that's very, very broad and involves a lot of different objects and people, because I find that that doesn't work as well as the SageMaker training job. And lastly, building a model from scratch is completely unnecessary unless you have to, unless you want to make something that's completely optimized and that's not there before. The SageMaker training job performs perfectly for this model, and I feel like that would be the best way to go from this point forward. So, in short, making the SageMaker training job would be the best method. Building a CNN using Keras and Tensorflow would be the second best, and then lastly would be using the AWS recognition service. Thank you for listening.